Good. Okay. Sorry for that. So just to give everyone a quick reminder of what I mean when I talk about floating point numbers, and there are quite different few formats out there now. There's actually way more, but I'm probably going to focus mostly on these four here, which is double precision, single precision, half precision, and then also this float 16. I may also call them float 64, float 32, float 16. And you can basically just see here, for example, how pi actually is encoded differently into bits and all of these different formats. And you can see they basically in the end, they just like a choice of how many exponent bits and how many mantissa bits do I want to use. Most computations obviously use double precision these days, but especially once we talk about GPUs, things get more towards the area of 16-bit. And yeah, I think that's basically pretty much known to everyone. But what I often find it's quite a good reminder is like how precise actually double precision numbers are, which is, I think, when I tried to come up with this example, I sat in my office at MIT, and I was basically wondering if I measure the distance to New York, let's say Empire State Building, how much could I actually how precise could I measure, could I distinguish 2 points on top of the Empire State Building on that distance? And the answer is actually you could distinguish each individual atoms. And just to give you that perspective of how incredibly precise these double precision numbers are. And so if you think about, I don't know, what's the distance I want to drive to New York, it's obviously like an absolute overkill, which is, don't get me wrong, it's still great because it basically meant that over the last decades, a lot of scientists could just treat floating point numbers as real numbers, and we could make basically a lot of progress because we basically didn't have to deal with all of that. But it also meant that we probably sacrificed a lot in terms of storage and computing resources and so on. And this is kind of what we try to tackle. Why we tackle it, and this is what I've sometimes thought about as the hierarchy of needs and for weather and climate modeling, where if you really go I don't know, at least 100 years back, people started making observation measurements and so on and started figuring out what are kind of the physics of the things that the weather and the oceans and so on, how that moves around us. And they started formulating that in terms of mathematics, wrote down some equations. Nowadays, we then discretize them and want to put them on a computer. And then we think oh, we have these discretized equations. Which computer do we actually run that on? But in the end, I feel like we have a lot of choices. People use different models, use different ways to discretize our equations. But in the end, at least before the generation of GPUs, everyone ended up computing that on CPUs. And so if that is actually the bottleneck, we should almost flip around this pyramid and say what are the things that we're really good at computing at, and then kind of walk backwards towards the kind of the mathematical model we want to solve in order to make the best or the most successful weather and climate prediction. And so just to give you an idea of what I mean by this, the funny map here, this is a map of low and high pressure systems produced by ECMWF, that's the European Center for Medium Range Weather Forecast. They basically produce the best weather forecast in the world. And this is a map that they published in 1979 of one of their very first forecasts. And they already used 64-bit floating point numbers back in what is that now, more than 40 years ago. And actually, they only changed 2 years ago down to single precision because they realized, hey, we can actually do everything a bit faster if we just do it in single precision. And so during that time, obviously, now we talk about digital twins. So we go basically from black and white graphs to digital twins where, well, you can guess which one is the satellite picture and which one is the model simulation of these two Earths. And so actually on the computing side, not much has changed since then. And only now we're kind of trying to catch up on all of these changes we're making. And I believe in the future, an institution like ECMWF might actually need to choose certain parts of their model or what they want to compute based on the architecture they have available. So really inverting this pyramid. Okay, we talk about precision, and the first thing I want to talk about is data, and then we come in the second part to the actual computational part of the actual processing floating point numbers in the second part. But let's talk about data. taking ECMWF again as an example, because weather climate forecasting is a pretty big institute. And this is the size of their data archive and how it's been growing over time. Probably like this figure is probably now like a year or two old. I'm not quite sure exactly where they are right now, but they're very, very close to the 1 exabyte barrier, meaning that they have a lot of data stored on, they're literally like tapes of that size. And they had to move their data, fun fact, they had to move their data center last year from Reading to Bologna in Italy. And guess how do you transport most efficiently these tapes, or like for 1 exabyte or almost 1 exabyte of these tapes? You literally like get a couple of lorries, put them all on the ferry of the channel, go over, then drive all the way down to Italy. So it's like, it's an enormous amount of data. And I kind of try to understand how much data has Google actually stored in all of its, the only estimate I found was from XKCD. And you can see kind of, yeah, approaching the 1 exabyte is kind of big. And so the question was always like, when does weather and climate data actually enter the Google regime? You see in the last years, there's basically been like a slowdown because people have started cleaning up some of the data, but otherwise, in the next couple of decades, ECMWF will definitely hit towards the 1 zettabyte regime, and this is you can do a lot of compression, as you can see on this picture, but resolution is also going to increase of all our models. So at the moment we're about like 10 kilometers, and you can just imagine if you go down to like 1 kilometer resolution, which you technically need in order to really resolve weather and climate well, you will produce so much data that we really have to start thinking about all of this now. So one of the questions that I've always been trying to ask is like, really, what information is there in a data set? So let's say you have just like, I don't know, a petabyte now of some zeros and ones, and that is the size of this data set is really spanned by like either like the precision that you use for all of these different numbers, the resolution you have to store your data at, also like the stuff like the number of variables. And so the question really was then, okay, how much of that can we actually chop off in order to, and this is what I call the real information problem of loss of data compression, in order to like, you want to find a small subset of this data so that whatever answer you want to get in the end, you still get qualitatively the same answer, right? So how much can I chop away so that your weather forecast still gives you the correct answer for tomorrow, and so that you not say like, well, this is absolutely wrong. It's not snowing right now. But this is, I mean, of course, I wrote this into an equation, but actually this is super subjective, right? So you may not know all the questions that someone wants to ask on a given data set upfront. Sometimes you're in a lucky position that, let's say, weather forecast has a very specific deliverable that it wants to say, like, we want to be the best forecast for rainfall tomorrow. And that might be a very precise application, and it might be much easier to figure out what this F actually is here. But in a lot of cases, especially with weather, with like climate simulations, you may just run a simulation into the future, and you kind of want to say like, well, now look into this data and do whatever research you want with it. And so it gets really tricky to find out what this small subset of that data somehow is. But we're trying to tackle the precision part, and so at least for that, I feel like we found a little bit of an answer to this. Which is motivated by this idea that if you have some kind of data, and this is what you see here in the top left is, I think there was nitrogen dioxide somewhere up in the atmosphere. You can see there's like different features. You see a little bit of the left of the figure is a bit brighter because that's where the sun was either shining or not shining, I can't remember. And then you see also basically some turbulence on it. You see that there's winds in the tropics that kind of blow things over in a different way as they do higher up and higher further down. But in the end, if you look at this data set, and if you were to display it in decimals, you would get something like this. And so the question I really wanted to ask, well, this is actually where this motivation for the research came from, is like, if I take which bit in this data set could I flip and give it to someone looking at it, and they wouldn't even realize that I flipped that bit. They wouldn't even realize that a 0 is suddenly 1 or it's not. However, in this decimal numbers that I put down, if I hit the sign bit and I suddenly flip the sign bit, then someone would immediately say like something is wrong with this data because suddenly, I don't know, humidity is negative and humidity can't be negative, right? So there's definitely some bits where no one would notice you changed something, and there's other bits where everyone would immediately see that something is wrong. And so if you think about it in terms of information, you can think about something as being like somewhat like real information and something more like false information that you could actually also just throw away. You wouldn't throw away essential information in order to do your statistics, whatever you want to do afterwards. And so translate, yes.
I think it's not false, but inessential, right? Non-essential.
Yeah, we talk later about false, and this is why I'll come to the point why I talk why I call this false information.
Okay. But the thing is, you're making the assumption that you know what the data is going to be used for into the future. So if you were to throw away data maybe 20 years from now, you'll say, oh, I wish I'd saved that.
Yes, exactly. So this is always the problem that we're facing. And so we try to come up with a way to find some kind of metric that tells us how much information to throw away to hopefully cover as many applications as possible. And so, but in the end, yes, it's very right. Like what I'm going to present on the next slides, people have basically told me like, oh, I have this use case. Does that still work? And you kind of have to make like somewhat like adjustments to that. Yes, absolutely. You can add these situations.
When you say uncertainty, are you mean uncertainty in measurements or in the information being used?
Yeah, this also really depends on what you're doing, right? So if that was the data that you see here, that was like completely uncertainty. Sorry, it was data from measurements. You may have your measurement device may give you already some kind of error bar on like, we can measure something to this accuracy. And so then obviously you directly know where your error bar should sit. And then you just throw away all the other decimal places that you, or like or bits that you don't know for certain. If it's a simulation, it might be very different because, for example, like a lot in weather and climate simulations, we don't necessarily know where our error bar is. And even if we, let's say, do something like an ensemble forecast so that we get our like probability of a certain event, you may want to keep, even if you say like, okay, this is actually uncertain, you still may want to keep these numbers because you afterwards you want to like assess still, even though you may say like, okay, I don't know whether the storm's happening, but if that storm was happening, I would still want to have a look at that storm. And you don't want to just like eradicate the storm because you know it's not certain. So I shouldn't keep it. Yes. So it's there's different aspects depending on which data you start from. But this is often where it gets really problematic because in like all the data that's stored at ECMWeb, a lot of that is like we don't know what the error bar is. And so we basically have this problem of like how can we kind of put an error bar to it, even though we don't know where it is? Can we somehow estimate that afterwards? And so what we came up with is this concept that's often called like bitwise information, with the bitwise real information content, or like bit information for short. It's based on this fairly simple idea that if you look at a stream of bits, just some zeros and ones, you assess the mutual information of these bits. And so in this bit stream here, you see that 0 is mostly followed by 0. Either if you have a 1, it either remains a 1 or switches back to 0. So if you calculate the mutual information of that, you end up with this joint probability matrix, and you can actually just throw this into mutual. This basically looks very similar to entropy here. You can see. And then in the end, you basically get a certain information out of that. And you can see here now, the information is not 0, meaning that actually, if you know which bit is the previous bit, it tells you something about the likelihood about whichever the next bit is occurring, right? If the zeros and ones were completely random, you would end up with 0 bit of information. If you always know for certain, basically, let's say, imagine you have like incredibly long stream of zeros and then an incredibly long stream of ones, then your information would be 1, because if you know you have a 0, then it's like almost certain that the next bit is also going to be 0. And we applied this to and basically realized that this is a nice way to distinguish between this real and false, and I still come back to why we talk about false in a second. And we applied this to gridded data because we said like, well, a lot of the data that we have will be somehow stored in like an array where every grid point is also basically like an entry in an array, so that the points that you have close in like in the real space will also be close to like individual values in your array in memory. And so we basically started doing this for all of the numbers in a grid data, some array, and we always looked at the sign bit, every exponent bit, and every mantissa bit individually. And so we basically came then up when like, well, if all of the bits are, for example, identical, like all of the sign bits are 0, then you actually end up with there's no mutual information because there's no entropy to start with. If you end up in a situation where a lot of zeros are kind of gathered together, a lot of ones are gathered together, then usually your entropy will still be 1 bit. But you also have the mutual information in between. However, the further down you go with the mantissa bits, and this is kind of like going back to what I showed before, this example data, at some point you end up in a situation where basically the bits just appear randomly. And so even though there's entropy, there's no mutual information, and this is why we talk about false information. That's not just to distinguish it from a real information, because both of them technically have entropy, but you can then with mutual information, one of them you can then talk about, like we call it like real and false information. And this is basically how we ended up, and this is like here quite a little example, how often we can analyze such a data set then. So we end up with this graph that shows you, well, the entropy is actually the gray line on the very top, and that is often pretty high, very close to 1 in many cases of our data. I mean, this is like positive only data. That's why, for example, the sign bit is not used. And then often we end up realizing that this real information basically drops down to a certain point where we say like, whatever we chop off at the end, we don't really care about anymore. Often you have to make some kind of sacrifice here. So like preserving 100% of real information is rarely practical. And so often we ended up like preserving something like 99%. So that basically this area here is 99% on compared to, well, and the 1% is then just down here. And so we call this in the end here down in the end false information because it still has entropy, but it is basically some of that we don't really care about. And so with this methodology, we actually ended up in a situation where we took a data set and then we were able to tell afterwards where should there be an error bar, like which are the bits that we should throw away. And we ended up basically just doing this by rounding. So this is exactly the way how floating point numbers are rounded, and we basically just round them to 0, which technically doesn't throw away any, or like doesn't free any memory, but you can then put the lossless compression algorithm on top. And the lossless compression algorithm will basically say like, oh, these are all 0, so I don't have to store them.
Just a quick question. I don't
Yes.
understand the beginning when you say in step 5, mutual information between bits. Which are the bits that you're getting mutual information from?
So you always do this for every bit position of your floating point number independently, right? So even though you have your grid data, and you may have the sign bit and the exponent bit stored next to each other, you say like, I only want to look at the sign bit of all of the values on your grid in your array.
Okay.
And then you do this entire analysis for every sign bit individually. And then for the first exponent bit individually, the second, and so on.
When you say the bit, you are doing every pairwise between all possible sign bits?
Exactly. So you have basically then you have a massive array of sign bits. You think of them as a bit stream, and this is actually you can walk in different directions, right? If you think about like a data set that is, let's say, like on the planet Earth, you may say like I want to walk in the east direction first, and then in the north, or you can do it in different directions. But in the end, you basically just unravel your array into a long vector of zeros and ones, a bit stream, and then you do exactly what I've shown before on that sequence of zeros and ones.
I see. So, but then the mutual information is a reduction in entropy due to knowledge of the prior distribution, right?
Yeah.
That's so. Where is the prior distribution in your sequence of bits? Is it this bit so far that you have a prior distribution that's predicting the future? The next bit, is that what you're looking at?
I think so. I think we're getting at some point. So in the end, your algorithm just counts the occurrences of 0 followed by 0, 0 followed by 1, 1 followed by 0, 1 followed by 1. And then you end with your joint probability matrix for every bit position, and you can translate that to the mutual information between adjacent grid points. How much does one grid point tell you about the next one? But does that make sense?
Maybe I'm just confusing it. Maybe you're saying all the prior bits till now are telling you about the next bit point. Or is it like if you look at the 200th bit position, the 201st, or it's 1 to 200 in the 201st?
Sorry, when I talk about bit position, I mean every single bit that you can have, let's say, in a 32-bit single precision number.
Okay.
But your data set may be as large as you want. So if you have a matrix of 100 by 100 entries, then you have 10,000 numbers in it. So for the signed bits, you would have 10,000 zeros and ones. And you do that checking which one is followed by which on those 10,000 signed bits. And then you do it independently on the next 10,000 first exponent bits, on the next 10,000 second exponent bits. So basically, it also means you don't have to throw in floating point numbers. You can throw in throw in integers if you want to. You don't make an assumption about the bit encoding. Yes.
Yeah, so I'm trying to get a sense for what kind of framework for meaning you're using on like what is real and false. And so it sounds like you're saying that real information is somehow continuous.
Yes.
And false information is discontinuous. Okay.
Which is not always the case. I absolutely agree with you. You can have data sets, and maybe I should have highlighted it a bit better. You can absolutely have data sets. So whenever we looked at, like, let's say spectral data, you technically don't have there doesn't necessarily have to be any relation between, let's say, the power you have at one wave number and the power you have at the next wave number. But this is kind of where we started with this idea of like grid data, because we said, okay, we know that in geospatial information, we usually have some kind of coherence. If we don't have that, at least in like weather and climate models, we often end up in a situation where if let's say your value jumps by like a factor of 2 from one grid point to the next, you may have that much uncertainty in this like factor of 2 that it doesn't matter whether you store the last mantissa bit. As long as you get this like factor of 2 right, jumping from one grid point to the next, that's all the information that is relevant in this case. That makes sense.
Okay, so we're relying on continuity of measurements we might want to take on the surface of the Earth.
Yeah.
Are there any examples of relevant measurements that might be discontinuous and that this wouldn't work for example?
Yeah, I think like spectral data, for example. We haven't figured out yet how to translate this, for example, to spectral data. But you could, obviously think about like transforming spectral data into gridded data again, doing the same analysis. But then it doesn't. I find it very tricky to think about this concept on like spectral data directly. Sure. Yeah.
Thanks.
How do you map this 3D grid into a 1D array?
So technically, you can have as many dimensions in your array as you want. You just have to. You have to basically define in which direction you want to walk through your array in order to unravel it into the single bit stream. So
when I say array, I mean the one-dimensional bit stream.
Sorry, say again.
I mean, how do you translate the grid into this single bit stream? How do you do normal?
So what we do. I actually realized for like most of the data that we have in weather and climate simulations is 2D, but then stacked into the vertical. And so it's often like also stored this way. So for most of the applications that we have, it's important to compress in the horizontal and not necessarily in the vertical. And so for us was the question like, yeah, well, does it matter whether we walk this way around and that way around? Often the way how our data is stored, it stores in the basically going from going eastwards first and then going either north or south. And so, but actually because a lot of the like in weather and climate simulations, a lot of the things are isotropic, so the direction doesn't really matter as much. And so it showed that basically it's way more costly to do the analysis, let's say in the north direction first, if your data in memory is actually ordered in the other direction, right? Because then you would need to jump all the time. You have like and so this is why actually from a practical point of view, we realized just walk how the data is stored in memory, and it probably gets you close enough. And that's where from a practical point of view, we just do it that way.
On the point about continuous data, does that have an issue when you wrap around? You go from the northernmost point to the southernmost point? And could that give you?
Yeah, it can. Yeah. So, but you can also formulate this algorithm with like mask data, for example. So there's right. I'm not going to talk about this, but there's let's say you have sea surface temperatures, and then suddenly you have land in between. Then you basically you can only then look at the bit pairs touching the coastline, but then you wouldn't continue through the coastline. even if it was stored, let's say, as like nonce or something, we would then just exclude those like looking at which is like where the zero is followed by a zero, you would just exclude that overland. Yeah.
So I could explain why when the n equals 1, 0 and 1 occur equally frequent.
Because otherwise your entropy, sorry, this is like you, the mutual information is bounded by entropy. And so your entropy is only approaching 1 if the chance, like if the overall probability of having zeros and 1 in a bit stream is 55-50-50.
Then how come 0 is certainly different to 0?
So like if in this example, if a 0 is very likely to be directly next to a 0, then you have a lot of mutual information between that. So if you know that you have a 0, then your next point is very likely also going to be a 0. But you would still need to have the property of this bit stream that both zeros and ones overall occur equally frequently, because otherwise your entropy wouldn't be 1. And so your mutual information is always bound by the entropy. So you don't have information to start with, and only when the mutual information is only like if you had no ones in the data set, that's the case for the sign bit, for example, in this example here, then you basically have no entropy to start with, and so your mutual information is also going to be 0, even though one bit tells you something about the next.
So there must be places where 0 is next to 1 to transit from.
Yeah, exactly. Yeah, this is why I kind of like drawn this here. It's like there's some zeros in this corner and there's some ones in that corner. Right. Yeah. Amazing. Basically, to like run through this a little bit now. We applied this because we wanted to see what this metric means. We applied this to some data sets from ECMWF, and this is actually some of these variables you can probably identify. There's like CO2 in there. There's like carbon monoxide as well. There's methane with CH4. There's something like ozone down here, and so these are basically a bunch of different chemical species, including aerosols in the atmosphere. And we have this data set, and we basically just like, okay, let's basically just apply this metric to it. And you can see that often you end up with a lot of information. The darker is more information in the exponent bits. Because these were chemical species, basically the sign bit was basically never used, except for this one, which actually I think was in the end also wrong. But that's the data set. And then often this information stretches somewhat into the mantissa bits. For some variables like CO2, it actually stretches really far into the mantissa bits, which I realized in the end is because CO2 is a variable that in the atmosphere changes basically never by much more than like a factor of 2. So we are now at around like 400 ppm. If you're like in an industrial area, it can go up to like 800 ppm or so. But it never actually changes much more. So we basically can encode CO2 without using any of the exponent bits. So most of the variations in CO2 require way more mantissa bits. And so this basically, looking at this, the main take-home message here for me is that actually the precision that we want on variables that we have in the weather climate model should be ideally very different depending on the variable. So just basically throwing, and this is kind of where like most of the weather and climate centers make it just easy to say like we use the same precision for everything, is actually technically speaking the wrong approach. But you would technically need to go into more detail. In terms of computing, that's a bit difficult. In terms of storing data, it's something else that's actually technically possible. And so this was really yeah, I think it was great for us to see that you can analyze the data from this perspective of zeros and ones and understand, oh, I should never like cut much more than this, and the error bar for another variable is actually quite somewhere else. And so basically motivated us to apply this to this, sometimes I call it information preserving compression, because based on that analysis, you try to retain as much bitwise information as possible and throw away some of the rest. And so here is an example where basically every of these slices of the planet, this is humidity somewhere halfway up the atmosphere, every of these slices is compressed in a different way. On the very right, we're basically in cartoon land, where you already see visual artifacts. That's probably not where you want to be. And this would be the case where you throw away about like 20% of the information, according to this metric. But then somewhere in the middle, you have like a sweet spot where you get quite high compression factors. So in this case, it was like 40 times smaller, but you actually still preserve at least 99% of your information. And you can kind of see that once you go further right, yeah, cartoon land starts, but on the left, you're still resolving everything to a degree where I did not find anyone who was able to tell the difference between them. And so we've implemented this into like my reference implementation is this bit information.jl Julia package, because as you probably realized, I'm a Julia person. But there's also a bunch of other Python packages for that. So if you're interested in that, absolutely like reach out and see if there's anything in there for you that's helpful. And then I want to kind of, unless there's any other questions, want to get a little bit more into this computing idea, because we're definitely in a time where we're transitioning from CPUs to GPUs for performance, energy reasons, whatever, but also GPUs basically mean for us that there's much more flexibility in terms of the data, the number format we're using. So not just like double and single precision, as it's, for example, on this laptop and probably most of other laptops here, unless you have like the GPU often also has some other format then on your laptop. But the ones we're actually talking about are more like these high performance GPUs with like, let's say the NVIDIA A100, which also has technically the float 16 and bfloat 16 on it. And this is where things get really fast once you go down to 16-bit. So for these A100s, I think you basically suddenly 32 times faster if you have this in these tensor core operations. And I think the new NVIDIA H100, I think last time I looked at the data, it was even like, I don't know, 64 times faster. I don't know exactly where they get all these like performance boosts from, but it basically means if you're able to go down with your precision, you'll benefit a lot from it in the coming decade or so. However, using low precisions can be quite challenging, and I would just want to get everyone on track with what I'm talking about. Give a couple of examples, which I've just basically simplified a little bit to show how this works. So let's say you have 1 and you add some number 10 to the minus 3. This you can add this in. We're now talking about half precision. However, and this is what we're the whole concept of stagnation. Once we add something that's even smaller than that, you obviously just end up with well, you can't add it anymore because it's whatever small increment you try to add, it's just rounded back. And then you can have situations where, for example, if you add 1, you add this tiny increment, you round it back, so subtract 1 again, you actually end up with 0, although it should be 10 to the minus 4, which can be, in some algorithms, absolutely devastating, and some algorithms may not matter, but you basically have to figure out for your algorithm, like, whether it's important or not. We do have problems like overflow and underflow once we go down. So something like 1,000 squares suddenly, boom, is infinity, or something like 10 to the minus 4 is 0. But actually, there are also some solutions available, right? So the first example, you can just reorder it, and suddenly you end up with the right example, with the right result. Or when we talk about underflow and overflow, we can apply something like scaling. So if you do it in a smart way, it may not even look as bad as it does here, which looks quite complicated. Like, why do you use square root of s and stuff like this? And it may get more expensive. But sometimes in algorithms, you can hide this somehow. You can put it in some places where you just say like, oh, all the numbers I want to compute, I kind of easily shift them into the range so that float 16, so half precision is not going to complain. It's not going to throw you like an infinity back at you, but it actually kind of just works. And so in this example, because I've scaled this equation, I'm ending up with something that's fairly close to what it should be. However, the first time, and this was like a long way to go, I think the first time I tried to use these 16-bit arithmetic on simulations, I ended up with a lot of problems, and I found that and this is why I show them, I find this quite illustrative to understand what's actually happening then under the hood. So the first one was supposed to be like an example of like some nice fluid simulation that was like affecting a little bit like what you see below, but actually it ended up that I had an algorithm that was always computing the position on a grid. And so I basically had advection preferably along the grid axis because there were some rounding happening in that direction. And so like just looking at this, I kind of realized what was actually going wrong. and was then able to correct for that. The next one was like a kind of like a diffusion of some heat that you have at the top of the soil, and it would basically slowly move down. And it's an example where your time steps tend to be super small. So you kind of have like tiny increments going up. And so you end up in this stagnation case where if I put it across, you basically end up with stagnation, sometimes directly in the beginning, sometimes a bit further down the line. But there are actually, and these are all kind of like little tricks, still using 16-bit in order to make this possible. Some of them are like using compensated summation, we'll talk about later a little bit. Some of them use like a little bit of like, let's say like a larger time step. And some of them talk about stochastic rounding that I also want to briefly mention. And so there are definitely many ways to solve this problem, even though, let's say, even if you only have 16-bit available. And so this is another example down here where technically if you don't know exactly what you're simulating, you may say like, oh, well, maybe both of them describe like a real world physics problem. But actually, it turns out in the right one, there's a lot of like spurious instabilities that shouldn't happen, which you can see then in comparison to double precision. And so these are kind of like, the examples of how things not to do right. And there's definitely a lot where I went through, a lot of pain I went through. Some of the other pain I went through is like whenever, because our systems are always chaotic. Not always, basically almost all of our systems that were simulated are chaotic. And once you go down in the precision, in these like very simple examples, like this is the Lorentz 63 system. So you probably know the butterfly, which chaotically jumps basically from one wing to the next, and then jumps back and forth. Once you use very low precision, you actually reduce the dimensionality of the attractor, and you end up with fairly short periodic orbits where it basically just keeps doing the same because there's not enough states that it can be in. And so it basically just keeps on doing the same thing. So technically speaking, you're basically rounding back the trajectory always onto the same trajectory that you were on before, because you can't resolve with enough precision the divergence of like one orbit or like the shadowing of one orbit to the next. And so stochastic rounding, it was then this one concept that came up and that I found quite interesting. And I think I stole these pictures here from Wikipedia, where let's say you have a grayscale image. If you were to just say like, well, everything that's somewhere between 0 and half, let's put this to 0. Let's put everything between a half and 1, put this up. So that would be round to nearest. That would be the equivalent of round to nearest, what we do with floating point numbers. But actually, if you were to do this stochastically, you end up with something like this, which kind of arguably contains more information than the face in the middle. And so it's really this idea that stochastic rounding you do proportional to the distance. So if you end up in between two representable numbers, and let's say you're like a quarter of the way, you would round at 75% of the chance you would round back and 25% of the chances you would round up. It's something that doesn't really exist yet on chips. There are a few chips where people are trying this. So Graph4, which I think are they still here? Okay. I think so. I think they're developing something like this. And so maybe in the future we'll have these like this new rounding mode directly implemented on chip. And I just want to give you a couple of examples of how powerful it can be. So here I'm just like switching on stochastic rounding, going from so in the same format, going from whatever was truncated to one down. You can see suddenly, because you basically every time you have a trajectory, because the stochastic rounding basically gives it like a little kick, you're actually able to explore the entire attractor. And the trajectories may get a little bit wobbly because of this like stochasticity that you end up injecting into the system. But it's kind of like on average gives you pretty good results. And this is where we got quite excited about this, because it might be like if it's well implemented on the chip, it might be like a fairly cheap way to effectively regain precision just by adding some adding some stochasticity. Which in weather climate we're a bit excited about anyway. And one of the things that really like blew my mind was this is probably have seen this before, like a logistic map where you have this like mapping of like you start with some x value, you have an r parameter, and you basically just step forward, and you in the end you have it's a chaotic system where you have these bifurcations happening. And so whenever you look, I think you look on Wikipedia or whatever, and you find these like fancy maps here of these like fancy graphs of these bifurcations, really showing how detailed this system can change depending on your R value. And the double and single precision, you get these nice pictures, but once you do this in float 16, basically your attractor kind of breaks down a little bit. And you also get like some equilibria here that shouldn't technically be there. But actually, once you switch on stochastic rounding, boom, you're back with your original chaotic dynamic system, which I found really interesting. Also played around with positive numbers that I don't want to talk about today. There's this log fixed point number that I was initially a bit excited about because it's a format where you don't have any rounding error or multiplication. But it turns out it doesn't really help. And then even if you use something as bad as float 16, which looks horrible, without deterministic rounding, if you switch on stochastic rounding, it does something much better. And so, yeah, it also turns out that because of this stochasticity, it kind of gets its exact expectation. So in practice, it basically means your rounding errors will be smaller than they would have been with deterministic rounding. And so we ended up basically stabilizing a lot of the simulations and removed a lot of the spurious stuff. And you can see that once you switch on the stochastic rounding, you're certainly much closer to where you should be with double precision. And so one of the things that, because stochastic rounding doesn't really exist yet on a chip, one of the projects that I've been working on, I think a year or two ago, was using this. We had access to this Fujitsu x64X chip. That is the processor that's also used in Fugaku, which used to be the world's fastest supercomputer, not anymore. But what we were excited about is that this Fujitsu had also half precision natively implemented directly on the chip, and so we were basically asking, hey, can we somehow make use of it, understand this? So we kind of understood like how can we use Julia on such a chip, because everyone always talks about Fortran and C and so on, and like can we use Julia for that? It turns out yes, super easy. It was actually even me, I don't know anything about compilers, but I still was able to do this. So for us, really, the question was like, how do we squeeze these equations into really only the area that we're allowed to play in the float 16, where like 65,000 is basically, well, that's the largest number you can represent, and otherwise it's game over. Same in the other direction, then these, because they're ARM architecture based, the subnormals are never really well supported. So if you hit a single subnormal, your performance immediately goes down. And so you kind of don't even want to have these subnormals. So like the smallest number you can have is 10 to the minus 5. But actually in the end, we found ways to scale this so that, I think it's a video. Yes. Oh, it's a bit laggy. So it's not supposed to be laggy. Anyway, but you can see that basically the simulation quantitatively gives you the same answer, whether you use double or whether you use half precision. This was possible because we realized there's some like nice techniques with Julia where we basically start writing really abstract code and we can throw in any number format we want, even number formats that analyze themselves while they're running. And so we basically started with this green curve and we realized, oh, we have a lot of subnormals, but actually we have a bit of headspace towards the nonce before we could get an overflow. And so then with scaling, like basically putting like a scaling factor S into these equations, we were able to find like a good compromise so that we kind of really match the numbers that we were calculating to match them to what float 16 can represent. And so instead of having, I think I have that on the same, instead of having like 10% of the numbers that would have been outside of the float 16 range, basically we're really able to drop this down to really make sure that all of the numbers we're calculating are actually in this float 16 range. From a computer science perspective, I also really like that because with Julia, you have this ability then to even formulate a number format that tells you where in the code is a certain number occurring. So we could basically just define this, basically put this in, and then it gives us a stack trace back saying like, in this line, I have found a number that is less than something. It's probably something you would usually do on a compiler level. But I'm not a compiler person. I don't know how to do that with compilers, but with Julia, it really feels that I can, as a normal user, it empowers me to do these kind of things and do these like little hacks. And I found that really, really powerful.
Sorry, I don't know if you can hear me. Can I just ask a question? What is a subnormal?
Sorry. So in floating point numbers, you basically have this typical definition of like you have exponent bits and mantissa bits, and the way how they are computed, or like how they translate to a real number this definition changes below what we then normally call the, like, either it's called like float min or like the normal number or whatever. It's basically this dashed line for the different formats here. And so for the subnormals, basically on the chip, what it means is that on every floating point unit, it would basically check, am I hitting a subnormal or am I not hitting a subnormal? So you basically in the chip, you have like a branching. And so for the x86 architecture, that's somehow solved in a way that it doesn't cause any performance penalty. But on these ARM chips, they basically said like, we don't like subnormals because it makes the silicon more complicated. And so they basically got rid of it, meaning that you don't have these numbers that are like either here in green for single precision, in this purple for B float 16, or in this part here for float 16. You don't have them available anymore. It's just like a very small range of numbers. For float 16, it would be between 10 to the minus 8 and 10 to the minus 5. That usually would be represented by these subnormals at a lower precision, but they kind of gradually represent your numbers towards 0. And if you ask me if we should redesign the IEEE standard, we should get rid of subnormals because I don't really feel that anyone's actually really benefiting from them. Does that make sense?
Yeah, that does. Thank you.
Yeah. Perfect. And then I think, yeah, I talked a little bit about compensated summation. So there are tricks where you can like kind of like slightly change your, let's say this is a room, I'll put a time step in. We can slightly change that and then compensate for your rounding error. We did this with this float 16. So even though you only use float 16, you effectively get more precision in a single calculation that you do. Here it's this addition between the U and like this update of in like a time integration. And that was very helpful because that also allows us to basically say like, okay, maybe we have some code where some of that's performance critical, some of that's precision critical, but the stuff that's actually only precision critical but not performance critical, we can cheat a little bit and regain some precision. And this is just the last slide that I want to show because this is what I've been working on in the last year. It's a project where I'm basically building an atmospheric general circulation model. Is called Speedy Weather. It's a bit laggy again, but it's a video that's playing. And at the moment, it's only running in single precision because the numerics behind it are way more complicated than what you've seen before. But my plan is also to make this possible to run on a GPU in 16-bit, maybe with stochastic rounding and these kind of things, and basically using Julia to make sure that you have a test, a platform where you can easily test all of these different stuff without going into old school fortran code with basically, I don't know, 95% of the people in my field are using. Thanks for listening.
Questions? Yes.
So I guess in climate simulation, one of the most cited arguments for using doubles is that we want to have conserved quantities and you need it for your conservation, mass, energy, humidity. And so people have done things where they go down to single precision or lower, and the pictures look good for maybe a day or a week, but all those little bits at the end of the numbers start to accumulate one way or another, and then we want to blow up. So I was wondering, have you run this sort of longer time steps and seen that it's, or no, sorry, not time steps, but longer simulations and seen that it remains stable?
Yeah, so for these much simpler shallow water simulations here, I have done that, and there it doesn't make a difference, which is basically the results from like technically your rounding mode is by 3, right? Because you have round to nearest, you have high to even, so that if you so that for technical practical purposes, you may end up rounding down, you may rounding up. But however, the way how often like these algorithms are formulated is that actually these like, let's say small updates to something suddenly matter. So if you have a systematic rounding in one direction and not like an alternating in one or the other direction, you absolutely may end up with these like non-conserving something. But that's why I'm basically usually saying like it's often a problem of the algorithm and the person. I know it's a hard job, but like they're finding out where do you lose that precision. I'm basically claiming I don't think it's impossible to solve that. especially once you go to stochastic rounding, because the stochastic rounding has really this property that it immediately avoids stagnation. Because even if you end up with like something that would be just like tiny update and you would round it back, you have a non-zero probability of suddenly rounding it up. And because it's so then like this exact an expectation, your budget may do something funny like this, but on average it will basically be should be back where it has to be. Yeah.
On the first part of the trying to work out which bits are significant in your data sets. I was kind of a problem I kind of come across recently working with kind of some ecological data was you have some rounding error. So you're doing floating points, some very small numbers creep in, and then these get all compounded because you're kind of summing across thousands of species. So what was below epsilon kind of rounding error becomes slightly more significant. And it's very hard for a human to spot, like when the numbers are not zero. The reason we spotted it in the end was because we had some things that should have been zero that wasn't, and it became very evident. But I was wondering, can you use this approach to say weed out that there is a kind of trough between the kind of those kind of cluster at the most significant bits, which is meaningful, then you've got where you not expect information, there suddenly is kind of you've got some noise in the kind of least significant bits that are kind of cropped in. Would that be able to kind of spot something there?
I'm not sure. I think like with a lot of these applications, I realized it doesn't necessarily matter that much what you do, but what kind of data you start with. So we even like had situations where, for example, inside the same data set, you would have basically something that's really smooth on, let's say, one part of the globe, and something that's really like much coarser, rougher on the other hand. Technically, therefore, you end up in a situation where your information content is different within the same data set. So you technically want to be able to analyze your information in this area and in this area separately. But definitely when it comes to, so you gave the example of like, you have some data set, you somehow truncate the precision down, and then you would want to do some operation on it. I think you would set like an average or like accumulating that. So technically, just from the floating point rounding perspective, it shouldn't make a difference because your rounding mode and the floating point numbers, like your rounding mode can go in both directions. But depending on the data set, you may exactly end up in that situation where like most of your numbers are round in one direction.
Yeah, pretty cool.
And then you exactly end up with this problem. What I found with like putting two parts of the talk together would be then in your case, I think it would be amazing if you could like truncate that down, but actually while you round it down to some lower precision, you would use stochastic rounding, and then you would actually go into like at this correct probabilities up and down, and then if you do your average in the end, you should end up exactly with the same thing. I don't, but technically the bit information concept doesn't really have, well, it's not based yet on stochastic rounding, but you could put it in, and it would be interesting in your case to see whether this solves it.
In the end, okay,
So I have an external question, which is you've been using this for weather and for climate. Is this being applied to things like huge databases of pictures, to financial institution data where we're just got loads of rubbish?
Yeah.
And
Yeah.
lots of.
So as I mentioned, also following up on one question here is like kind of what we started with as like this is kind of the data we're looking at, is this idea that you have some kind of like geospatial information that has some kind of like spatial coherence of like if you, I don't know, if it's really warm over the UK, it should also be warm over the Channel, maybe still somewhat warm over France. And so you have like a deep correlation length scale in
So you
space.
have that in connected markets, but you might not have that in pictures, for example.
Exactly. So if you once we talk about pictures now, and I guess it depends on what pictures are we talking about, right? If you think about pictures of, I don't know, New York, of all the skyscrapers with a lot of little bobs and bits here, that might not work. If you talk about pictures of like, I don't know, vast landscapes, it might absolutely work. And so it's
So family, not families, but yes, maybe. Thank you.
yeah, I think it's always
Oh, yeah. So you talked about it a little bit with the shallow water equations part. But when it comes to climate, obviously the kind of stochastic nature of the subgrid plays much more of a role than it does in some sort of deterministic fluid equation. Have you looked from a dynamical systems point of view how important or how unimportant those additional terms are in the false information, where even if two deterministic pictures might look different, their physics is actually two plausible trajectories, and even though you've made this truncation, this is still a valid trajectory, even though you've made this truncation. So not from not from a information point of view, but from a valid physics point of view. Have you had a look at that?
Quite difficult to think about an example where you would have that.
So speedy weather, take that for example. If you make some sort of small perturbation that might be lower than your rounding error, you're going to get two different dynamics over some time scale.
Yeah. Say you would do the same simulation that's shown in the end in double precision. Suddenly your weather eventually would look different, right?
Yeah, exactly, which isn't a problem.
Yeah.
But a lot of the comparisons you made, you kind of looked at one picture here, and deterministically how close they look. Have you looked from a kind of dynamical systems point of view how unimportant those additional bits are when it comes to the climate side?
Yes, you can sort of see that when you plot the bifurcation diagrams. The gaps will tell you what you've lost in some cases within.
Yeah, I mean, this is obviously like these bifurcation diagrams, they really only work with like very low dimensional systems. And something like a shallow water system, you would have already like, I don't know, depending on your resolution, you would have like millions of independent variables that you can't put into such a graph. But still, and I wrote this down here. So in this situation, because the shallow water system is still relatively simple, I realized at some point, and there's like a bit of analysis you can do, but I realized at some point that basically a lot of the rounding error was kicking in the continuity equation and was basically causing the flow to be not as balanced in terms of its geostrophic balance in that case. And so you actually ended up, and this is where these whole little wiggles came from, is that it actually caused gravity waves. So basically, because you have a rounding error, you ended up basically like moving your pressure in the shallow water system somehow in the wrong direction, where then on the next time step, it was like, well, you were unbalanced, I need to kick up the gravity waves. And suddenly you had these gravity waves that actually started blurring the otherwise quite smooth fronts. And so, yes, you can have situations where rounding errors suddenly cause the dynamics of the system to be very like different, right? So in that simulation would have way more gravity waves than you would otherwise have. It's an interesting thing to try to understand how the physics can change of the simulation that you once you go down to your precision. But again, this is also something that then with these tricks of like scaling it correctly, doing like the compensation sum and so on, you can actually basically get rid of them again and solve them. But it's an absolutely interesting, like I wouldn't know immediately, let's say if you go to a more complicated system, let's say like speedy weather, you have like 3D, you have like clouds and rain and all of this stuff to immediately spot of like, where am I killing some of the physics because I'm using low precision. But I guess that's the beauty of research, we'll have to find out.
Thank you. Okay, we should have the last question.
I think presumably, if you sort of calculated RMSE over time, you'd see it kind of going up.
Yeah, but like in this case, the gravity waves usually, the gravity waves here, they cause like some mixing. But if you look at the gravity waves, or like if you look at velocities, for example, usually if you like gravity waves are surprisingly irrelevant for a lot of the phenomena that we have in the atmosphere or like in these systems. They do play obviously a role, but this is where like a lot of the models do some kind of implicit time stepping, trying to step over the gravity waves and so on. And so you actually may end up in a situation where you cause more gravity waves or you cause less gravity waves, but you don't necessarily lose much of your, let's say, ability to predict 10-day weather accurately into the future. And so you may well end up with a useful model, even though you've changed physics inside it.
Okay, thank you.